Hi there, my name is Anne McCormick. I'm a software engineer at Cisco, and I'm here to talk to you today about a project we're working on to scale DHCP and DNS by providing a dnsmasq alternative. So let's first do a quick overview of DHCP and DNS. DHCP and OpenStack provides tenant virtual machines with IP addresses and some fundamental configuration, including DNS server addresses, gateway and router configuration, and host routes. DNS and OpenStack provides tenant virtual machines the ability to find each other and to find critical services in the network by name, and also allows reverse address resolution, meaning if they have an address they can find to the name, and access to a DNS server for resolution outside the tenant network. And today in OpenStack, DHCP and DNS service is provided by a tool called dnsmasq. It's open source software, initially released in 2001, and it's adequate for small deployments, but as we'll see, as the cloud starts to scale, we start to have some issues. So first, let's take a look at an example architecture. We've got a green tenant down here, a blue one down here. Each tenant has a tenant network. The green tenant has 2 virtual machines, blue has 1. And so over here, we've got our Nova nodes with the virtual machines. Up here, we've got a single network node. And each tenant network has a network namespace and a dnsmasq process associated with it. So initially, when the network node comes up, the DHCP agent configures the dnsmasq processes. And what it configures them with is the range of IP addresses to be assigned to the tenant VMs, as well as the configuration to push down to them. All right. Now let's pretend like this smiling VM down here in the green tenant is just coming up. He's going to send a DHCP request up. It's going to make its way through the network namespace up to dnsmasq. dnsmasq is going to assign an IP address and send that down, as well as configuration, back down to the tenant. For a DNS request, it's going to follow the same path up to dnsmasq, and one of 3 things can happen here. Either dnsmasq can be authoritative for the domain that the tenant VM is requesting, or it can have the information cached, in which case it'll send back down the response immediately. If neither of those is true, dnsmasq goes out to the configured DNS server, gets the information, sends it back down to the smiling tenant.
When would it be, I'm going to ask a question. When would it actually be authoritative?
It would be authoritative for anything that's in that tenant network, any of the other virtual machines and perhaps some services. Okay, so let's talk about scaling the cloud now that we have our basic architecture down. As OpenStack becomes the cloud platform of tomorrow, we need a DHCP and DNS solution that's going to scale. And now let's talk about the problem of scale with dnsmasq in particular. First, let's talk about service availability. Back to our example architecture with our green and our blue tenant. So the green tenant has 2 virtual machines, and each one of those has a port in the network namespace. Let's start adding some more virtual machines. Each one of those adds another port to the network namespace, and each time a new port is added, the dnsmasq process has to be restarted. And while it's down, if any other VMs come up, they're not going to be getting their IP addresses or their configuration, and DNS requests aren't going to be answered, so there's an outage. The second problem of scale is process overhead. So we're fine with 2 tenant networks. We've got our green and our blue, 1 dnsmasq process for each, no big deal. But what happens when you start to add more tenant networks and more tenant networks and even more tenant networks? Well, for each tenant network, you've got a separate process. If we start to talk about tens, hundreds, maybe even thousands of tenant networks on a network node, that's a lot of process overhead. So how do we plan to fix these DHCP and DNS scale problems? One way we could do it is to relay the DHCP and DNS requests to an enterprise server. We could have 1 relay per network node, thus eliminating the process overhead that we see with dnsmasq. And as virtual machines come and go, the relay would stay up and running so that there would be no outage. Back to our example architecture, but this time, dnsmasq processes are replaced by a single relay in the network node. Let's take a look at what happens on configuration. The DHCP agent is going to configure the relay, and all the relay really needs to know is how to talk to the enterprise server. And the DHCP agent also configures the enterprise server with the same sorts of things it would have configured dnsmasq with, the range of IP addresses and the configuration to send down to tenant VMs. All right, now our smiling VM is coming back up again. He sends a DHCP request up to the relay. The relay sends it out to the enterprise server, who then assigns an IP address from the range of addresses and sends that along with configuration back down to the tenant VM. So once you get into a topology like this with a centralized DHCP and DNS server, the first problem you're going to hit is that there's going to be overlapping subnets between tenants. Tenant networks are meant to be isolated in OpenStack, and this provides a problem. So how are we going to address it? Well, we're going to make use of DHCP VPNs and DNS views. DHCP VPNs are an IETF standardized way of segregating a DHCP broadcast domain. And DNS views are a similar concept, but it's not standardized, not yet standardized. So we'll have one DHCP VPN and one DNS view per tenant network, thereby isolating them. The centralized enterprise server can now differentiate between tenant networks. And the relay can send the responses back to the requesting tenant networks. So what does this look like? As the network node comes up, the DHCP agent configures the relay in the enterprise server. And what it's going to do is configure in the enterprise server a DHCP VPN and a DNS view for each tenant network. So you can see that they're isolated the way that they need to be in OpenStack. So what are some of the desired qualities that we're going to need in an enterprise server? Well, the first thing that comes to mind is carrier-grade stability and high availability, and also service provider scale for large deployments. We're going to need multi-tenant support, like I talked about, so that the tenant networks are isolated. A flexible deployment model, where you could either run the server directly on the network node or elsewhere in the network, depending on your needs. Something that can be monitored through a user interface for operator ease. And something that can be configured through a REST API so that the DHCP agent can get it up and running. And a server that has all of these qualities is the Cisco Prime Network Registrar, and this is what we use in our architecture. So it's all well and good to talk about this in theory, but how do we know that it's actually going to scale? What we're seeing in our scaling tests, for example, the first graph on top, average time needed to receive a DHCP lease. What we're seeing is that as more and more DHCP requests per second are made, dnsmasq starts to have a much higher response time. It starts to go up around 1,000 requests per second. And if you get to 10,000 requests per second, which by the way is kind of an ungodly amount of requests, but it's just meant to prove a point, dnsmasq starts to take an average of 94 seconds to respond to a DHCP request. So that means it's going to trigger retries, which is going to exacerbate the problem. Now, alternatively, in blue here, we show the CP&R response time. It goes up a little bit, but even at 10,000 requests, which again is just a ridiculous amount, it's only taking on average 100 milliseconds to respond to a request. Let's take a look at packet drop percentage. Again, as DHCP requests per second goes up. What we're seeing is that for dnsmasq, around 800 requests per second, it starts to experience loss. And if you extrapolate all the way out to 10,000 requests per second, it experiences 100% loss. Basically, none of the initial requests, no retries, nothing's getting through. Your tenant VMs aren't coming up or anything. But alternatively, in blue, we see CP&R. Right around 2,500 requests per second, we start to experience some packet loss. And extrapolate all the way out to the ridiculous case of 10,000 requests per second, it experiences 61% packet loss, meaning things are still getting through. Initial requests and retries, things are still coming up. So that's it for DHCP and DNS. And if you'd like to learn more about Cisco technology and solutions for OpenStack, please stop by the Cisco kiosk or ask any of the Cisco people walking around OpenStack today. Thank you very much for your time.